Okay, in this video presentation, we will recap what we've seen in Module 5. And in my opinion, there are kind of just two topics in Module 5. I kind of wrote here over here sum of squares, basically, especially as they pertain to the partial f-test and the topic of multicollinearity. So we'll review those ideas, right? So far, in multiple linear regression, right, we've seen the following hypothesis tests, right? The t-test, which basically enables us to answer the question of whether we can drop a predictor from the model, right, while leaving the other predictors in the model. And the ANOVA f-test is, right, can we, right, simultaneously drop all of them, or is our model useful in predicting the response variable? Notice neither of these tests allow us to assess if we can drop a subset of the predictors simultaneously, right? So, right, if you have k predictors, and again, let's assume we are working with just the first order models. Now, question is, if you want to drop between 2 and k minus 1 predictors, what can we do? Right, because the t-test and the ANOVA f-test will not allow us to assess if we can drop between 2 and k minus 1 predictors. Now, let's take a look at just this example. So this is just the data set that we've seen before from the 1976 NFL season, and it had 9 predictors to predict the number of wins a team has. And if you take a look at the output over here, very often what people will be tempted to say is that if you look at all these predictors, right, almost all of them other than x2, right, the rest are all insignificant. So the question could be, well, could we drop all of them based on the t-test? Now, the t-tests do not inform us that all of them can be dropped from the model. What this t-test tells us is we can drop x1 while leaving all the others in. That's the key point. It's while leaving all the others in. So collectively, we can't use the t-test to say, hey, can we drop 8 of these simultaneously? So there is the partial f-test. So the partial f-test allows us to assess if multiple predictors can be dropped simultaneously from the model. It works under this principle where we are measuring the change in the SSR or the SS residual with the removal of these predictors from the model. Right, SSR measures how well our model fits, right? So the change is in some ways allows us to assess, right, how much improvement there is in the model fit. So a few key ideas that we're using. As long as we have the same response variable, the total sum of squares is a constant, because the total sum of squares, if you look at it from a formula perspective, it's basically, right, the difference between yi and its mean squared all up. None of these values are dependent on the model, right? They are independent of the model. So that's fact 1. Fact 2, SS total equals to SS regression of that model plus its corresponding SS residual. So based on these facts, each time predictors are added to the model, the SSR increases and the SS residual decreases by the same amount since the total sum of squares stays constant. Right, so really what we are assessing in the partial f-test is to see, is the increase in the SSR or the decrease in the SS residual significant with the addition of predictors? So the partial f-test, right, always works in this situation. I always like to think and write out what my full model is, right, and what my reduced model is, right? So the reduced model is the model after dropping your predictors, some predictors, right? And so in effect, right, the null hypothesis is basing the coefficients for some predictors are 0, right? And these are the ones that you're considering to drop, and the alternative is basing at least one of the coefficients in the null is non-zero. Now in words, what the null means is that we favor the reduced model, right? And the alternative is basically saying we favor the full model, right? So it's basically a comparison between a reduced and a full model. So if you end up rejecting the null, it means you support the full model, and if you fail to reject the null, it will say let's go with the reduced model. So notationally, sometimes I write the full model as F and the reduced model as R. As a quick reminder, right, what the formula is, the partial F statistic is basically the difference in the SS regression between the full and reduced model. This whole chunk divided by R, where R denotes number of terms to drop or number of predictors to drop that you're looking to drop, divided by the SS residual of the full model divided by n minus p. And take a note over here, this is the number of parameters in the full model. So this is how I like to think about the F statistic. The reason why I like to write it this way is that we're then going to compare with an F distribution. An F distribution is always like a ratio of two fractions. So you notice there's a fraction here and there's another fraction there. And each fraction has its own degree of freedom, right? So the df1, the first one is R, and then the next one is n minus p. So I like to write it this way because it reminds me that this is the comparison I'm making with the F distribution with R and n minus p degrees of freedom. The textbook replaces this whole denominator with ms residual of the full model. Same thing, it's just I prefer my way because it reminds me what this value is that I need to compare with. Equivalently, you would notice that as the numerator over here, SSR of the full model minus SSR of the reduced model is equal to the SS residual of the reduced model minus the SS residual of the full model, because of the fact that we talked earlier on, right, that SST is a constant value. So the change in the SSR will be the same as the change in the SS residual. Right, so that's what the partial F test allows us to do. So that's really, right, one topic that we've looked at in Module 5. The second topic that we've looked at is this topic of multicollinearity. So this happens when predictors are nearly linearly dependent on each other. So what are the issues here? The main issue is when your predictors are nearly linearly dependent on each other, then your estimated coefficients will have high variance. When your estimated coefficient is a high variance, that means the estimated coefficient may be very different from the true value of the coefficient, right? So in this setting, then one needs to be careful with interpreting the estimated coefficients in the usual manner, right? Because it may not be that close to the true value. Because the estimated coefficient may be very different from the true, then there's a chance that the estimated coefficients could be very large. Also, a byproduct, the algebraic sign of the coefficient could be different than from what is known theoretically, right? So if it should be a positive relationship, you might end up with a negative slope just because your estimated slope is going to be far from the truth. Adding or removal of one or more data points could result in large changes in the estimated regression coefficients. So the main issue with multicollinearity is this issue of high variance with the estimated coefficients, and the usual way in which we interpret the coefficients, the slopes, have to be very careful. From a purely predictive standpoint, predictions are fine, but you must be especially careful with extrapolation. How do we detect multicollinearity? So if you know that predictors that do influence the response, but you have insignificant t-tests for them, and yet you have a significant ANOVA F test. So remember last module I said the ANOVA F test is usually not very useful. Well, this is one area where it's useful, where you know there's a whole bunch of insignificant t-tests for your predictors, but an ANOVA F test that is significant, that's indicative of multicollinearity being present in your model. There are other ways to assess it. High VIS. The textbook uses 10 is the threshold. If you read other books, they might say 5 or 4. That isn't this strict threshold, in my opinion. The key idea, though, in my opinion, is if you notice a high VIF and then you take steps to remedy the issue of multicollinearity, do the VIFs drastically reduce? Are they drastically reduced? That, in my opinion, is the key. This last point may or may not detected all multicollinearity all the time, but high correlation between pairs of predictors. So if you have that happening, then multicollinearity is present, but if multicollinearity is present, this issue is not necessarily true. So if you look back at the NFL example, right, a lot of insignificant t-test over here, but if you look at the ANOVA f-test, very significant, right? So this fact is indicative of, it indicates the presence of multicollinearity. And if you take a look at some of these predictors and you think about what they measure, it makes sense that multicollinearity is present. What are some solutions? So you could use a subset of predictors. So among those that are linearly dependent on each other, drop some of them, keep maybe one or two of them, right? And that's the method that we'll be using the most over here. There are some other methods that we will look at later on in the class, and you will look at later on in the program. Dimension reduction methods, which simple principal component analysis is one of them, and shrinkage methods are some solutions. However, I will point out the following. A few slides ago, I said, right, the main issue with multicollinearity is that it impacts the interpretation of your regression coefficients, right? So in terms of exploring the relationship between your variables, your predictor with the response, that's going to be a big deal. Dimension reduction methods and shrinkage methods do not necessarily help with improving the interpretability of these coefficients, right? So what these do is they can help improve predictions, but prediction itself is not a huge issue with multicollinearity, right? So these two help improve predictions, but the main issue with multicollinearity is the interpretation of coefficients. So if you are really interested in exploring the relationships between the variables, then your course of action should be the first bullet point.